Okay, folks, good afternoon. We have a new homework assignment posted on Blackboard, which is due on Tuesday. This one is a computer simulation kind of a homework assignment, so you have to use either Simulink or Plex or whatever you feel comfortable with. Now, my advice would be, if you want to talk to other students, go ahead and talk to other students. But after you talk to other students and you find out what their correct approach is, your first step should be open up MATLAB and click on a kind of a new, let's say you want to do Simulink file, okay? Don't borrow anyone's file, because if you do that, I can find it out using MATLAB again. So please start with a brand new file that you have created. And then from there, you develop your model. It's okay if your model resembles someone else's after you have talked to them, that's fine. But again, the file should be created by you, okay? That's very, very important. Please pay attention. I have zero tolerance for that. If I find out that you have borrowed someone else's file, even you have deleted everything, and you started from scratch because it was borrowed from someone else to begin with, then I won't give you any credit, okay? All right, so that was about the homework assignment. Any questions? Yes.
So what about the control part of the homework?
It's open loop. It's just put two sources of pulse a square shaped signals as your input. It's not a close. We are just trying to simulate the power stage, not the control stage. So like D1 and D2, or the phase angle or the phase shift between D1 and D2 is basically two independent sources. Yeah, exactly. Other questions? Okay, so what we did last time was we started the discussion of matrix converters. Let's take a look at them actually. Let's see. So as it turns out, most converters are a special case of the matrix converter. The simplest example was the bridge rectifier. And in matrix converters, you have several lines of input, which are usually in the stiff sources of voltage, like a three-phase source or a single-phase source or whatever. And on the output side, again, if it is a single-phase or three-phase, you have a bunch of lines coming out that are usually connected to a stiff source of current, for instance, an inductor. And then you are using a single pole, multiple throw kind of a switch over here to select which one of these throws are actually at any given time, which one of them is connected to the output side. And as I just said, this switch could be in either of these positions, but it cannot be in two positions at the same time. So that means at any given time, only one of these switches that have actually, have a red circle around are engaged or turned on. And for the inductor or the output current to be continuous, you got to make sure at least one of them is on, basically. So at any given time, one and only one of them is on. Switch realization, it depends on the application. It depends on if, for instance, VI2 is always larger than VI1, or there is a chance that VI1 could be larger than VI2, like if it is an AC signal or DC signal. And also it depends on the direction of your output current. Is Iout1 always positive, or it is like an AC signal that is sometimes positive, sometimes negative. So because assuming that we don't know anything about the converter, the most general case would be using a 4-quadrant kind of a single pole, single throw switch, which is actually shown over here in two different forms. Then I was going to explain one of the applications of a matrix converter, which is actually the most common application of the matrix converter. And we ran out of time, so let's take a look at it now. So a lot of times, if you are trying to run an electric motor and at the same time you want to control the speed of that electric motor, that means the signals, the AC signals, assuming it's an AC motor anyways, like an induction motor or something like this, the frequency or the amplitude of the voltage signal that is applied to this electric motor should be variable so that you could actually control the torque and ultimately control the speed. That means you cannot directly hook up your source that is available to you, which is fixed frequency, fixed amplitude, to your three-phase motor, even if you have a three-phase source available. So one common approach is to rectify this. Then you need a power factor corrector that we're going to discuss after we're done with matrix converters. Then at the end or in the middle, you have some sort of a DC signal, like 400 volts, 1,000 volts, whatever it is, depending on the power. And then use an inverter. So you're basically having these cascaded converters one after each other, and it does the job. The jobs are kind of decoupled from each other, like the inverter does not interfere with the operation of the rectifier or anything. The only problem is you're using too many converters. Your cost is going to go up. The power efficiency is going to be low a little bit because you're rectifying the entire power, then it goes through a power factor corrector, then the entire power goes through the inverter. So you're processing the power in several stages, therefore your efficiency would not be extremely high. One approach to avoid this would be using a matrix converter. So basically a matrix converter kind of does all the job that these three converters in cascade would do. Although I'm not sure if it does power factor correction or not, so let's just have a question mark on that. But anyway, it directly converts three-phase, if assuming that you have a three-phase source available, it directly converts the power or processes the power supplied by a three-phase source to a three-phase load, and we are does it. So that's why this topology or this kind of matrix converters are called sometimes direct frequency converter. Okay, so that's where the name comes from, direct frequency conversion. All right, so that's where the term comes from. Now, if you happen to choose to do it this way, most of the times, and we are about to see why, this only works if your output frequency is lower than your input frequency. So if your line frequency is 60 hertz, your output frequency should be lower than that. In other words, it should be a very low speed electric motor. So a very low speed, a very high power electric motor. So that is pretty much the target for the application for these kind of converters. So let me write it down here. So one note is that the output frequency is variable, and we are going to see that. But at the same time, it is less than the input frequency. Okay. Then the other note, as I explained, the efficiency would be improved compared to the indirect frequency conversion. And the other thing would be in the top approach, as you can see, there is a capacitor, which I call it the energy storage device, but it's usually usually an electrolytic capacitor. The lifetime of these capacitors sometimes are not very, promising. After a while, usually the component that is needs a replacement is the capacitor, because they do age and they are sensitive to high temperatures. So in this method, we don't need no need for energy storage. Or basically caps. Okay? So we are curious to know, well, there is this approach out there. We are curious to know how they do it. So let's take a look at actually the details of this matrix converter that takes a three-phase source and converts it into AC. Yes?
Is it how we can say that input frequency should be greater than the output? Why is it always output frequency is lesser?
We are going to see this most of the times, yes. Although the question is, do you want to have an AC, a sinusoidal AC signal on the output, or a square-shaped AC signal on the output? And we're going to see that sometimes you can actually achieve frequencies that are higher than the input. But if your desired signal is a sinusoidal signal or a signal that is as close as possible to the sinusoidal form, it is usually lower than the frequency of the line, basically. And we are about to see that. Okay. So in this example, in order to make things a little bit simple, I am just assuming that my output is only single phase, okay? So a matrix converter with single phase okay? Okay, so I'm assuming I have three phase of AC power is available to me. So lines A and B and C. And then I have two lines on the output because it's a single phase thing. So okay, so I'm labeling these switches to be A1 and A2, although A1 and A2 are not complementing each other or anything, just because they are connected to line A, I'm just calling them A1 and A2, then B1 and B2, and then C1 and C2. And this is our output voltage. Okay. All right, so A1, B1, and C1, you know, that rule applies that any given time, only one of them should be on, one and only one. And also for A2, B2, and C2, same story. So I have three states on the top row and three states in the bottom. So 3 times 3, I have a total of 9 possibilities. For instance, if A1 is on and B2 is on, then the output voltage, okay, let's take a look. A1 is on and then B2 is on. So V out is VA minus VB basically, okay? Or VAB. So it's a line-to-line frequency of VAB. And then, for instance, if B1 is on, so we have to pick one switch from the top and then one switch from the bottom. And then A2 is on. Then okay, so let's see. B1 is on, and then A2 is on. So V out is VB minus VA, or VBA. Okay, and for instance, if A1 is on and also A2 is on, so A1 is on, A2 is on, so technically it's like we're shorting our output, so our V out is 0. And you can keep, considering the other 6 possibilities. 6 out of these 9 possibilities are giving us line-to-line voltages like VAB and VBA, VBC and VCB, and VAC and VCA. And the other 3 possibilities are just giving us 0. So 9 possible states. So we have 6 of them are line-to-line voltages, and 3 of them are 0. Okay. And by the way, we are using a 3x2 matrix converter here. Okay. So what the conclusion that we are reaching is, depending on the need, depending on where we are in terms of synthesizing the output voltage, if I want the output voltage to follow, for instance, VAB, all I have to do is just turn A1 and B2 on. If I want it to follow 0, I can turn A1 and A2 on, or B1 and B2 on, or C1 and C2 on, and so on and so forth. Now, last time I had some handouts. I'm going to use them now. Hopefully you guys have it with you. Let's see. I saved them here. Okay, they are here. Also, if you're a distance student, these files are also uploaded on Blackboard under a name called Matrix Converter. Okay. So if you look at the sequence of phases, all right, so if you assume you have, for instance, voltage of phase A with respect to the ground as your reference, and then VB is following that with 120 degrees of phase shift behind, and then VC is ahead with 120 degrees. And then line-to-line voltages in terms of magnitude are a square root of 3 times these guys. Like this one is VA minus VB or VAB. Okay. So if you look at all of these 6 line-to-line voltages, the sequence of these are going to be, I'm just going to write them here. It doesn't really matter which one it is, but I'm just going to write them here. So this is VAB. The next one would be VAC. Or, AC. And then we have VBC, VBA, VCA. Unfortunately, we are running out of space here. VCA and VCB. So like this is this one, this one. Okay. And the sequence repeats itself, okay? So after VCB, we have VAB again, okay? So these are like 60 degrees apart from each other, and then they kind of repeat themselves. So let's say I am at a particular operating mode in the system, and I would like my output voltage to follow VAB. For instance, let's say this is my desired output voltage. Okay? I'm trying to generate or synthesize a very low frequency output voltage. So when, for instance, my output voltage is very small and for some weird reason my output voltage is synchronized with VAB at least at the very beginning of my graph over here. So I have to follow VAB. So all I do is I turn A1 and B2 on. Therefore, my output voltage follows VAB, and that's actually shown over here. I'm following VAB. Okay? Then time goes on, and I don't want to stay on VAB for long because, as you can see, VAB is rapidly growing large, and you have a DSP that is actually doing all this math and realizes that now it is time to follow, for instance, VAC. So it turns, I don't know, for VAC, we got to have A1 on and C2 on. So we turned it on, and now for this portion of time, we are following VAC. All right? And obviously, there is a transition that our output voltage jumps from one line-to-line voltage to another line-to-line voltage. Then time goes on a little bit, and then we decide that, depending on the reference that we are using, or the modulation, it's not directly a modulation, but the switching scheme that we are using, that we have to follow VBC. It's over here. Okay? So overall, we can follow any of these guys as we want, and the logic behind following them is to minimize the error between the actual output voltage, which is the blue curve, versus the ideal output voltage, which is the red curve, okay? So there is some controller over there. It's actually reading this error or the square value of this error and then maybe integrating that error. And then based on that and some predictions, it makes choices, okay, follow VAB. Now you should follow VAC. So it's possible to do that. So as you can see, you can generate an output voltage that is really not AC, but it is as close as possible as we can to our reference, which is an AC signal. Okay, something like this. First of all, observations. It is happening at lower frequencies. So you can see our signals are repeating themselves a lot during one period of the output voltage. So for instance, if our line voltage is 60 hertz, the signal that we are synthesizing is probably, I don't know, maybe 10 hertz or something like that. The output voltage is not exactly AC, but remember, a lot of times we need this signal to apply it to an electric motor, and that electric motor has an inductor on the input side, so it actually filters it out. So your output current is almost AC. So your output current is going to be something like this. All right, something like that. So there are some sudden jumps in the input voltage, and that creates a little of a ripple in your output current. But overall, you can argue that your output current is a good quality, low frequency AC signal. So we achieved the goal that we were trying to do. That was use a matrix converter and the simplicities associated with it, and generate a current that is almost AC low frequency. So the application would be, remember, this doesn't work everywhere, so application would be usually we do it for high power applications. High power, low speed, like motor drive. Motor drive. Maybe I should add single phase too, because if it is three phase, you got to use three of these matrix converters. Although three-phase approaches are possible too, no problem there. Okay, like for instance, you have a mine and there's a conveyor belt or whatever it is, or some sort of an elevator or whatever. It's very low speed kind of a thing and very high power, so you use three-phase power to do this. Now, if you are worried about these sudden jumps in the output voltage, like over here, there are, again, depends on what kind of a quality of output voltage waveform you want. There are transformers that are called phase shift transformers. So it's like a delta Y kind of a combination, one of the power system tricks, and you can actually use those transformers to create 12 phases rather than 6 phases. Over here, we only had 6 phases, 6 line-to-line voltages. But using a phase shift transformer, we can actually generate up to 12 phases. So then your resolution would be even better. I mean, if the resolution is really, really important to you. Okay, any questions? Yes?
If it is a high power application, the voltage will be much higher, right?
The input voltage? Probably. Go ahead.
So if we are continuously switching on and off this AC circuit, will there not be a very surges or something like that?
There will be, yes. So that would be another problem to solve, and that would be, for instance, adding low-pass filters to the input side. Okay, but you're right. In terms of input current, that could be actually a good class project or homework assignment, drawing the input current of each individual phase. And unfortunately, it doesn't look nice at all. So yes, somebody has to fix that if the utility company is unhappy about it, or maybe you're locally generating power, and then there is too much stress on your local generator.
In fact, if we are opening the circuit when the current is not zero, generally we open the circuit breaker in AC circuit when the current is zero and voltage is maximum.
Okay.
So if we are opening our switches when the current in a particular phase is not zero,
okay,
then there will be a current chopping. And
there is going to be sudden, so your input currents are discontinuous because of exactly what you mentioned, because you're jumping from one current value to another, basically, like from 10 amps to 0 or vice versa. But then you need to have some sort of a low-pass filter to make it palatable to your input, whatever your input is. Is it the power grid or your generator? That's correct. Yes?
Is the frequency continuously variable?
Unfortunately, yes and no. You have, so technically we generated this. So let's say if you want to slightly increase your frequency, you can, for instance, generate a signal. Okay, let me pick another one. Yeah. You can still synthesize this one too, but you have a limit. You know, you cannot go beyond the frequency of your line, or maybe 3 times the frequency, or 1/3 of the frequency of the line. Okay, so if your frequency gets too close to the line frequency, then your jumps are going to be less frequent but more severe. So the resolution gets bad, basically. So ideally, you want to have a very low frequency signal. You know, something that it takes forever to ramp up, and you know, something like that. So the lower the frequency, the better the resolution is. Okay, other questions? Okay, so let's talk about disadvantages. One is too many switches. So technically we use 6 switches, but switch realization could be more challenging. Too many switches. Okay. The other one is a commutation between switches, and I'm going to explain it. Okay, so for this particular example, let's call this I out. And as we can see, I out is supposed to be continuous. But at the same time, for instance, initially we were following VAB, then we got to follow VAC. If we are following VAB, that means A1 should be on and B2 should be on. And then we want to switch to VAC, that means A1 is still remain on, no problem, but then C2 should be on. So that means at this particular time, at this particular jump over here that I have highlighted, we have to instantly turn B2 off and C2 on, okay? So it should be instant. There shouldn't be any overlap between them because otherwise we are shorting phase B to phase C. There shouldn't be any dead time between them because then in that case the output current is not going to be able to be continuous. So it should be very, as soon as we turn B2 off, C2 should turn on, and that becomes a problem. Commutation means moving from the status or conduction of one switch to the other. So commutation becomes a problem. If there is too much overlap, we are shorting the phases. If there is not enough overlap or there's too much of a dead time, then the output current is going to be unhappy. So because of that, you have to put some auxiliary like capacitors and snubbers and resistors around your switches to basically take care of this very, very transition that you are trying to manipulate. So that's the main problem over here. We have too many switches and instantly we have to jump from one switch to the other. So that becomes a challenge. Now,
I have a question.
Yes.
Can you repeat why the low frequency application is more appropriate in this?
Oh, the high frequency application is almost impossible. For instance, if your objective is to generate an output voltage that is, let's pick a color here. If your output voltage should be high frequency like this, you don't have enough time to follow a phase and then jump to the other phases. So it becomes very, very difficult, or your jumps are going to be too large, basically.
Or maybe slightly less than the frequency, 60 Hz frequency.
A slightly less than 60 hertz. So technically, for instance, okay, let me draw it. So this is a slightly less. You are pretty much almost following one of the phases, right? So it becomes, so for a long time you're going to follow a phase, then all of a sudden jump to another phase. It's possible, but then is this really very practical or not? I don't really know, because then you're creating a lot of very low harmonics in the system. That may actually become a problem.
Is it possible by creating more waveforms with lesser phase shift and having high frequency?
More waveforms? What do you mean by more output waveforms?
More input waveforms.
Oh, okay. But yes, as I said, if you use a phase shift transformer that is, physically generates some tricks, and not only your VAB and VAC are there, we also have 30 degrees phase shifter. So we have 12 of them in each cycle. So you have a better resolution, and therefore you can actually create a higher quality output signal, basically.
What about frequency? Higher frequency?
Frequency you can, higher frequency, again, frequency here should be still smaller than your line voltage. I would say at least 2 or 3 times smaller. Okay? However, we are about to see another trick that we can use to achieve a higher frequency, but unfortunately it's fixed. It's not a variable high frequency using this topology. So let me go to another page of the handout. So one of the applications or advantages of these converters is that they are a little bit versatile in a sense that you can use the same converter to give you an output voltage. Let's say all of a sudden you want the same converter to give you an output voltage for a particular application. All right, so here, let me just highlight the phases one more time. So let's call the phase sequences before I do this, let me copy the third page as well. Okay. So remember the phase sequence is VAB, for instance. Then it is VAC. Then VBC. Then VBA. Then VCA. And then CB. Okay. So technically, any signal that you want, as long as it is within this area, you can see which one of these line-to-line voltages are closer to what you want, and then basically jump from one to the other if need be. Let's say, for instance, my objective is to generate a DC output voltage. Okay, ideal output voltage. And then I can say, okay, in this time interval, let me use blue. I will follow VAB, then I will follow VAC, then I follow VBC, and just keep doing that. Okay? And there you have it. You can actually have a relatively good output voltage in which the ripple is only 360 hertz. So your line frequency is 60 hertz, but the ripple and the output voltage is 6 times that, so it's easier to filter that out. Now, if you say, oh, wait a minute, I didn't want this output voltage, I wanted an output voltage that was a little bit smaller than this. For instance, something like this. Then what you got to do is you got to follow this pattern. Let me see if I can choose it. You can, for instance, follow this line, then follow this line, and then, for instance, jump up. let me see if I can do it more reasonably. All right, let's follow this and follow this. And then we have to jump from one to the other. All right, something like this. So again, as you can see, the ripple in output voltage has increased, but on average, it is giving me output voltage that is a little bit lower than what I initially wanted. So actually, you can even regulate your output voltage. Okay, it doesn't have to be fixed value. All right. And again, in terms of versatility, you can create a crazy-looking output voltage like this, for instance. This particular one is a square shape, but then you can argue that it is an AC signal anyway, and it is a high-frequency AC signal. Okay? So did you really need an AC signal that is a square shape, or did you need an AC signal which ideally had to be sinusoidal? So you can argue that looking at the fundamental harmonic frequency of this guy, it is something like this, and actually the frequency of the signal is higher than the line frequency. So again, you can even achieve higher AC signals as well. The highest that you can achieve without having a very, very messy switching scheme would be, let me see if I can do it over here, something like this. Follow this, then follow this, then follow this. So technically, you can actually achieve an output voltage that has a fundamental frequency that is 6 times larger than your line frequency. Okay, so 360 hertz. So technically, you can generate anywhere as long as you don't want to generate an output voltage that is here that has no cross point with your line-to-line frequency, line-to-line voltages. You can generate any, like a triangular waveform, or I don't know, trapezoidal waveform, or something like that. So these are the some of the applications or advantages of the matrix converter. Any questions? As I said, they are not very common because of their disadvantages, but every once in a while you go somewhere and say, what is this? It's the matrix converter. They're actually using it. Okay, if there are if you don't have any questions, let's move on to a new topic. And that topic is power factor correction, or in general, power conditioning. Okay. Oh, so it's abbreviated as PFC, basically. Okay. A lot of times, our main source of electricity or power is the power from the power outlet or the grid, which is an AC signal, which is a sinusoidal AC signal. So let's say we have a 50 hertz frequency here. And then a lot of times our load does not need AC power. For instance, TVs or computers or laptops or cell phones, or even if you have batteries to charge, they operate based on a DC principle, or they are DC devices, DC loads. So you have to rectify this AC power into DC, and as we are about to see, it actually creates some nonlinearity in the load. Okay. All right. And we are going to see why. So basically you have like a diode bridge rectifier, and then your load is a nonlinear load. Ideally it should be like almost like a resistance, basically. So Ohm's law applies, and your voltage and current are always proportional with each other, but unfortunately that is not the case. So once you actually look at the harmonics of this electric current, they don't look so good. So if you look at your voltage, the spectrum in your voltage, ideally you should only see 60 hertz, which you usually don't because of the nonlinear loads. And then if you look at your current, they are all over the place. So we have like the fundamental harmonic, then twice that, then 3 times that. So you have a lot of harmonics. The other thing is this graph doesn't show if this component is in line in terms of phase angle with this or not. Okay, so that's another thing that we have to worry about. So our current, we have a fundamental harmonic at 60 hertz, but it may not be in phase with your actual input voltage. So that's another thing to be concerned about. Okay? And that is bad. So why is this bad? Because once you are drawing a lot of harmonics from your source, utility companies are going to be having a problem. For instance, the local distribution transformer may get saturated because of these high frequencies. Okay. The other thing is extra losses. So if your current is not in phase with your voltage, that means not only you're drawing real power, you're also drawing reactive power. And it's not really power, you're not really consuming it, but that means sometimes you're actually getting extra amount of current from the grid, and sometimes you're not getting as much current from the grid. And that extra amount of grid that you're drawing, that means the RMS value is going to increase, and therefore your losses is going to increase. So power system people or utility company would say, if you have a load and you're connecting your load to my network, it should be, the current that is drawing, it should be purely sinusoidal. And the power electronics people may say, we don't care, we just want to get the job done, we want to rectify this, and you should have provided DC power to us, for instance, to begin with. So in order to resolve this conflict, there are some standards. The IEEE has set forth some standards. European countries have, or even in Japan, we have several standards. So technically, if you are a manufacturer of a device that is being plugged into the network, it has, depending on the power rating of your device, it has to comply with certain standards, like IEEE standard. I don't really remember the number of those standards. Like if you look at the back of your power supply for your computer, you see a lot of logos and symbols. Those are actually the name of the standards. All right. So, so we are trying to resolve the problem. The question is, what are the solutions that we have to actually, instead of having such a current, we have nothing here, and actually our fundamental harmonic is even in phase with the input voltage. Okay, so that's our ideal goal. So let's look at the solutions. So the whole thing is we got to put something, either change the behavior of the load, which is usually doesn't happen. So we got to put something here that kind of provides a buffer between the source and the load, right? So let's call it the power conditioner. All right. Okay. Before power electronics was maybe cheap or reliable, they relied on passive approaches. Well, passive approaches mean that put a filter, basically. A passive filter that would allow the 60 hertz fundamental harmonic to pass through and would actually attenuate the rest of the harmonics. Now the problem with using a passive filter is, because your frequency is so low, it is only 60 hertz, the size of the elements that you need to use, which are capacitors and inductors, are going to be very huge. So you're looking at something that is relatively large and bulky and probably expensive. The second approach that power electronics actually offers is active approaches. Okay. Active means there is some sort of a switch in your system. then you can subcategorize that into active filters or power factor correctors. Okay, and I'm going to explain what an active filter is. But before that, active filters are divided into three subcategories, that they are shunt, or they are series active filters, and maybe a combination of both, which is called shunt series. Okay. And then you can subcategorize each one of them is it a voltage driven or a voltage source or a current source? Is the device trying to emulate the operation of like a stiff voltage source or a stiff current source? And also, when it comes to power factor correctors, you can divide them into two categories. One of them is multi-stage, and then single stage. And we're going to see what they are. Okay? So, I mean, there are different ways of categorizing things. So this is my approach, how to categorize the general concept of power conditioning. So in case you're curious, okay, what is a shunt active filter? Let's talk about it. By the way, these active filters are different than the electronics active filters. In an electronic circuit, when you say an active filter, that means you're using operational amplifiers. Here, that means you're using a power electronic converter. So let's talk about, for instance, a shunt active filter. All right. So you have this source, which is an AC source, sinusoidal, and then you have this nonlinear load. I'm just showing it like this, like it's nonlinear. Okay. Which is drawing some, non-ideal current from the source, I load. And then what we do is we use this power electronic converter over here. Okay, let's call it I sub F, as in filter. And we control the power converter in a way that IF plus IL, which is the total amount of current drawn from the source, is sinusoidal and in phase with Vn. Okay. So if we take the power converter out, only IL is drawn. And IL, because your load is nonlinear, IL has a lot of undesired harmonics. But what we can do is we can actually add a power, add a pseudo load over there, which is our power converter, and then draw another current, which is called IF, so that IF plus IL is basically sinusoidal and in phase with the input voltage. Okay. Now remember, this power converter should not really consume this current. You're drawing current from the grid. That means you're kind of consuming some power. But then assuming that everything is AC, then you can argue that on average the power that the power converter is consuming should be zero. In other words, your power converter somewhere needs to have some sort of a capacitor or maybe batteries, some sort of an energy storage system that sometimes you're drawing current or drawing energy, sometimes you're sending energy. On average, you're not really dissipating a lot of power over there. So this is the very basic idea of shunt active filters. In power systems, there are converters like this, like a megawatt kind of a scale. But that's not really what we are going to cover over here. In terms of power factor correction, what I'm going to cover is the most classic approach of like a low power, you have a TV or a computer or a power supply, you're trying to hook that up to the power outlet, and you would like your current to be as close as possible to a sinusoidal form. So this is more like an introduction for you guys. We don't really cover shunt active filters. Now, in case you're curious about series active filters, let's also talk about that for a little bit. So the whole thing that this was called shunt was because it was being placed in parallel with the load. Now, you can do a dual of this thing and place a transformer on the path of your input current. So this is your nonlinear load. Okay, and then you are using your power converter, you're synthesizing a voltage, which I call it VF. So the power converter is connected to let's call it the primary side, and then VF is actually added to your load voltage on the secondary side of the transformer. Okay. So again, this power converter is really not providing power. It's sometimes charging and discharging its capacitors. But overall, it is kind of synthesizing a voltage that is added to the load voltage. Okay. So this time, you're actually controlling this voltage instead of controlling the current. So and by the way, you have your grid, for instance, here. So this time your control logic is different. So this time you're trying to make sure VF plus VL, the load voltage plus your active, basically series filter voltage, it is sinusoidal. and in phase with the input current. Okay, so this is all about a series active filter. If you want to compare a series active filter and a shunt active filter, you can instantly say that maybe series active filter is not as efficient, and the reason is the entire load current passes through the primary side of this transformer. Okay, so on the primary side of this transformer we have extra losses, whereas in the shunt active filter this current had nothing to do with the load current, and the load current has nothing to do with your power converter. They're kind of in parallel with each other, so they have nothing to do with each other, so there's a little bit of an efficiency gain over there. But I mean, there are so many dynamic equations, and you can argue one could be better than the other in terms of dynamic performance and things like that. Any questions so far? All right, so we haven't really got to power converters yet, power factor corrections yet. Any questions? All right, so now let's talk about power factor correctors, which is the main focus of our discussion. So power factor correction. So these two that we talked about were one of them was sitting here, the other one was sitting here. Now we want to talk about these guys. Okay, now these devices, power factor correctors, are usually cascaded with the load. And for that reason, that means if your load is, for instance, consuming 100 watts or 200 watts, that entire power is passing through your power factor corrector. Therefore, they better fit low power applications, because if you're talking about megawatts of power, you don't want to add another converter on the path of a megawatt power. So you have to go after these shunt or series active filters. So these PFCs, they better, so the application would be low power applications. Okay, so give you guys an example. So we have this nonlinear load. And then you have this source, which is AC, and then you place the PFC in between. Okay. Okay, something like this. So by putting this guy over here, you're hoping that your input current is supposed to be, ideally, is sinusoidal. And in phase with Vn. Okay, something like this. If this is your Vn, you would like your In to look like this. Okay, something like this. All right. Any questions? Okay. So let's talk about, we keep talking about this nonlinear load. So let's talk about this nonlinear load. What is this nonlinear load? A lot of times, as I said, this nonlinearity comes into the picture because we are trying to rectify the AC power into the DC so that our load would be able to use that. So let's talk about it. So when it comes to nonlinear loads, the first one would be bridge rectifiers, or rectifiers in general. Okay. So what is that all about? Let's take a look at it. So remember from power electronics or industrial electronics or whatever, let's say you have a load that consumes DC power, and then you use a bridge of diodes to hook this load up to your AC source of power. Okay, oops, that's not how it's supposed to work. All right, so this is connected here. All right, something like this. And so if you have forgotten about this, this bridge of diodes, the way it works is when the input voltage is in its positive cycle, this diode turns on and this diode turns on. So we are drawing power and kind of charging the capacitor. Then when the cycle reverses and the input voltage is negative, this diode turns on and this other diode turns on. So again, you're still charging the capacitor, okay, even though your input voltage is negative. So you're symmetrically drawing power from your source. So looking at some of the waveforms, let's call this your input voltage. Okay, and then this is the rectified version of, or this is the, rectified version of my input voltage. And your output voltage is going to look like this. So it follows this peak and then goes down, and then follows this peak and then goes down. So your output voltage looks like this. Okay, so when it is following the peak, that means the diodes are on. Otherwise, the diodes are off, and therefore the capacitor is just getting discharged through the load. Looking at the input current, remember, in the end, we care about the input current. There are a bunch of equations involved, but your input current, actually, you're drawing power only from this point to this point. It's like an impulse of current. And then similar story here. My drawings are not very symmetric, so this conduction interval is a little bit wider, but in practice they should be identical. So this is going to be your input current. And then this kind of repeats. something like this. So as you can see, our input current is nothing close to being sinusoidal, okay? First of all, it's 0 for a long portion of time. And then when it's, for instance, positive, it's like a spike of positive, and then 0, then a negative spike. So it is not sinusoidal. And not even in phase with Vn. Okay? So we got a problem. So in many applications, we would like to rectify the voltage of the utility power to give us some DC voltage and then consume it in our load, for instance, in a computer or in a TV or many other applications, or like a microwave. We tend to use diode bridges because they are very simple. There is no switch in them, so you don't really have to control them. It's just 4 diodes, so they do a very good job. But at the same time, our input current is kind of awful. Basically, looks kind of awful. So we got to do something about it. So that's actually what we are going to discuss. A few options of providing a power factor corrector. So technically, at the end of this class, you are familiar with a device or a power electronic converter, which turns out to be actually a boost converter that sits in here and basically gives you an input current that is looking much nicer, basically. Before even we get there, we got to make a bunch of definitions, like what is actually power factor, like an engineering definition, and what is total harmonic distortions. And we don't really have time to do it today. I'm going to actually do it next week. So remember about the homework assignment that is on Blackboard. It's very easy for me to find out if your file has been originated by you or not. As I said at the beginning of the class, in case you were late, your first step should be open MATLAB and click on a new Simulink or Plex model, and then put your model in there. So it should be originated by you. You shouldn't borrow someone else's model and make modifications to that. Please don't do that. All right, see you guys next week on Tuesday.